Hey, we went over endothermic reactions. Endothermic reactions have a net absorption of energy, and an exothermic reaction has a net release of energy. We looked at what is happening during a reaction, and this is all frozen for you. There we go. We looked at what is happening during a reaction, and you get two molecules coming together. You form an activated complex where bonds are breaking. When you break bonds, you what? Does it take energy or release energy? It takes energy to break a bond. When you form a bond, it releases energy. Okay. And then we looked at endothermic reactions and the potential energy diagram. So you get this reactants are on the left-hand side. They have a certain potential energy. This hump is called the activation energy, EA. The peak of the hump, I guess, the bump, whatever you want to call it, is the activated complex. That's kind of represents what that is. And then they start to form bonds. As they form the bonds, they release the energy, and so your potential energy comes down. Okay. Now, how far down that goes depends on how stable the products are and if you're having an endo or an exothermic reaction. Because this finished at a higher spot than the reactants, this is an endothermic reaction. And we call the overall change in energy delta H. We call it enthalpy. And change in energy is potential energy of the products, basically whatever this number is, minus the potential energy of the reactants. So 40 minus 20 in this case gives you 20 kilojoules. If your delta H is positive, it is an endothermic reaction. Okay? So up in here, right here, delta H is positive. Whoops. Energy's been absorbed and it's an endothermic reaction. Okay? We say that endothermic reactions are non-spontaneous because you're adding energy to get them to move. Okay? Is there any questions about the diagram? How to recognize what's an endothermic reaction? Basically, if the products end at a higher spot than the reactants, you know it's endothermic. Okay? In a chemical equation, how you represent that is you put the energy. Well, there's two ways to do it. You can put the energy in the equation, in which case it's positive. We know we have to add energy to the equation, so it's in the reactant side. So potassium chlorate plus 41 kilojoules of energy breaks it apart into potassium and chlorate. Okay? You can also represent it by writing the equation and then putting delta H off to the side and saying it is positive 41.4 kilojoules, indicating that you have to add energy into the equation. Okay? Examples of endothermic reactions: photosynthesis takes energy to happen in plants. Breaking water into hydrogen and oxygen, that is not something that happens naturally, which is a good thing. All right? Like spontaneously, I guess I should say. This is going to take energy to happen. We don't want our water decomposing into hydrogen gas and oxygen gas. That would not be good for anything because both of those are highly flammable. Okay? All right, so that is endothermic. Now exothermic. Exothermic, you're giving off energy. Okay? So when it takes energy to start it, but you get more energy out at the end. So that's all the big explosions that you saw we did the other day that you all love. All right? It leaves the surroundings, usually if it's heat energy, warmer than you started with. And if delta H is positive in an endothermic reaction, what's it going to be in an exothermic reaction? Negative. And we'll see that in the diagram. And we say that exothermic reactions are spontaneous. Because once you get over the energy hump, you'll see that energy is enough to activate and keep the reaction going. Okay, so exothermic reaction. We start with our products. Start here. You have to add in energy. So there's the activation. Okay, you get to the peak, and then we start to form bonds and release energy. You get more energy coming out. So you fall down here at the reactants, or the products, sorry. So here are your reactants. Here are your products. Again, whoops. Again, this is the activated complex here. So if we call this 50 kilojoules, we call this, I don't know, 60. I'm just making numbers up here. And we call this, we'll just call it 20. That doesn't look like a proper scale, but that's okay. So if I said, what's the activation energy, the EA? That's going to be that distance there, right? That's the that's the EA from where you start to where the top of the peak. So it's going to be 60 minus 50 is 10 kilojoules. Activation energy is 10 kilojoules added to get this reaction going. What is delta H? How do you figure out delta H? It's always going to be energy of the products minus energy of the reactants. So potential energy of the products minus potential energy of the reactants. Potential energy of the products is 20. Potential energy of the reactants is 50. So we get negative 30 kilojoules. Okay. If your delta H is negative, it means it's an exothermic reaction. Okay. All right. In the equation, okay, if you're going to write it in a chemical equation, you're releasing energy, right? Energy is going out into the atmosphere. So your energy symbol, or how much energy is released, must be on the product side. Okay, because it is a product. One of the products of this reaction is energy leaving the system. Okay, so now you don't write negative here. The negative is just the overall delta H, but when you put it into the equation, it's always positive when you write it on that side. Okay, so So when you put it into the equation, it's going to be positive because this reaction says if we burn methane, which is what we did with the bubbles the other day, this is the same reaction we did. Methane gas plus the oxygen, we lit it. So the flame that we used was the activation energy. Once I lit it, it formed new bonds, formed carbon dioxide and water, which released a whole bunch of energy. That energy was then used for the rest of the methane, and we can use that energy as the activation energy. So that's why we call it spontaneous, because it goes. Whereas an endothermic reaction, if you pull the heat source, the reaction will stop. Okay? But once this starts going, it goes until all the gas is used up. So we get 50 kilojoules produced as energy, and that's what we felt, the warmth that we felt. The other way to write this is you just write the chemical equation, then off to the side, you say delta H, and then when you write it this way, you have to put the negative sign, because the negative sign is indicating that it is an exothermic reaction. Sorry? Yeah, if you don't, you have to have that so that it doesn't look like it's in the equation, but I guess the delta H would indicate that. If you put a comma, I'm fine with that. Just as long as it doesn't look like it's in here. Because if you're going to put it in the equation, you have to write it like this. Okay? Is that okay? No? Oh, that would make sense. Sometimes they write it, they'll just put plus energy on the product side. Right? If it's on the product side, it's an exothermic reaction. Okay? If it's on the reactant side, if it says plus energy over here, it's endothermic. Okay? All right, so what I will expect you to be able to do, okay? I will be asking you to be able to identify if it's exo or endothermic based on the diagram. All right? So if we end at a lower spot, it's exothermic. Right? If delta H is negative, it's exothermic. I'll ask you to calculate the energy of activation, which is just the peak here, the difference between the peak and where it starts in the reactants, and delta H, which is the difference in energy from the products and the reactants. Okay, I'm going to ask you to calculate those. And an endothermic reaction, your products are at a higher level than your reactants. Okay, and then again, calculate EA and delta H. All right. Is that okay? Do you think we could do that on a test? Yeah, just nodding. All right, we got one last thing to do here, people, and then this unit is over. I'll give you some practice questions. It'll be a straightforward day today. Okay. Don't worry about those hazards ones. I'll give you practice in a sec. All right, rates of reaction. How to speed up a reaction. Okay. So as soon as you see the word rate, you're talking about the speed. Well, you can't write in highlighter. The speed of the reaction. A rate problem is talking about velocity or speed. So how fast a reaction occurs. Some reactions are slow, some reactions are faster. How can we speed it up? So what is the rate of, what is a reaction? What does it depend on? What is happening when we have a reaction, a chemical reaction? What's happening to the molecules? Why do they react? What do they do to react? They collide. That's basically what it is. So if you want to speed up the rate of a reaction, increase the frequency of the collisions. So if you increase the number of collisions, how often they're colliding, the rate should go up. The other thing is you need to have enough energy in the collisions, right? The right orientation and enough energy. So so you have to have enough energy in the collisions. Okay. So what can we do to increase the frequency of a collision? What's one way we could speed up the number of collisions or speed up the molecules? Sorry? Increase the temperature. If you increase the temperature of a reaction, the molecules move faster, they hit more often, and they hit with more energy. So increase the temperature. So they collide more frequently, they have more energy, so more of those collisions actually break bonds. All right, what else? Can we think of anything else? Catalyst? Catalyst? What a catalyst does, I'm not going to ask you to reproduce this, but what it does is it lowers the activation energy. So if you're looking at a potential energy diagram, let's do an endothermic reaction. There. So there's your endothermic reaction. If you add a catalyst, what it does is it lowers, this is the catalyst, it lowers the height that you have to get over. So instead of having to go all the way to here, now we just have to get to there. So it takes less energy. So the reaction speeds up. In grade 12, you talk more about catalysts and things like that. All you have to know is that a catalyst will speed up a reaction. But this is how it does it. And it does that. I think I talked about enzymes before. They will grab the molecule and orientate it to the best geometry so that when the collision happens, it's hitting in the right spot. Okay? And that's how it speeds up the reaction. All right, catalysts. There's two others that we can look at. Anybody come up with another one? Sorry? Squish them? Make them more condensed. So we would say increase the concentration. Okay? So increase the concentration. If you increase the concentration, so for example, you're going from 1 molar, I'm just making up a thing, 1 molar HCl, and you increase it to 5 molar HCl. Remember, molarity is moles per liter. So we have 5 moles every liter instead of 1 mole per liter. There's more particles in there, so they can collide more often. And that equals more collisions. So you can increase the concentration. And there's one other method.
Add energy by shaking.
Sorry?
Add energy by shaking it.
That would be, that's true, but that's kind of tied to temperature. Your temperature, energy, same idea. But that's what I did with the thing, exactly. We did it with the last one I did where I threw the powder into the fire. Remember I tried to light it when it was on the bench? What do you call that? What? Surface area. Yeah, you increase the surface area. Okay. If you increase the surface area, you get more frequent collisions because they're not all tightly bound. You get more collisions. Okay, and there's other sort of sub ways to do this. Okay. Like for gases, increasing the concentration can mean decreasing the volume. Talk more about that in grade 12. That's more grade 12 stuff. For right now, all I would expect you to be able to do, if I said, how can you increase the reaction rate? Temperature, catalyst, concentration, surface area. Surface area does not work for gases because gases don't have a surface that you can increase, okay? So this is for solids. All right. Okay. That is the unit, peoples. So let me just